There is a question so fundamental that even silence seems to lean toward it. Why does anything exist at all, rather than an eternal, undisturbed nothing? Philosophers have whispered it in candlelit rooms. Physicists have traced its shadow through equations that describe the first fractions of a second after time itself began. And children have asked it plainly, staring at the stars, not yet knowing they had stumbled upon the deepest mystery any mind can hold. It is not a question with an easy answer, perhaps not a question with any answer, and yet the asking itself opens something vast and quiet within us. If these slow journeys into wonder bring a kind of peace, staying subscribed means more will find their way to you. Now, let the mind grow still, let the breath soften, and let this oldest of all questions carry us gently into the dark. We begin here. Perhaps you remember the night it happened to you, though the details may have grown soft around the edges with time, the way childhood memories tend to do. You were lying in bed, and the house had gone quiet, and somewhere between wakefulness and sleep a question arrived in your mind that seemed to come from nowhere and everywhere at once. It was not a question about homework or about what would happen tomorrow or about whether you had remembered to brush your teeth. It was something else entirely, something that felt both very simple and impossibly large, and it settled over you like a blanket that was somehow too heavy and too light all at once. Why is there anything at all? You wondered. Why is there something instead of nothing? And perhaps you lay there for quite some time, turning this thought over and over the way you might turn a smooth stone in your pocket, feeling its weight and its strangeness. The question seemed to resist being put into proper words, and yet it also seemed like the most obvious thing in the world to ask. After all, here you were, existing, in a room that existed, in a house that existed, on a planet that existed, in a universe that stretched out in every direction farther than you could possibly imagine. All of it was simply there, humming along in its quiet way, and it occurred to you, perhaps for the first time, that none of it had to be there at all. There could have been nothing. There could have been no room, no house, no planet, no you lying awake in the darkness asking questions that seemed to have no answers. And yet here everything was, stubbornly and mysteriously present, and you wanted to know why. If this experience feels familiar to you, then you are in very good company, because human beings have been asking this question for a very long time indeed. We have records of people puzzling over the existence of existence itself stretching back thousands of years, across cultures and continents and languages, and there is something rather comforting in knowing that the question that kept you awake as a child is the same question that kept philosophers and poets and priests awake in ancient Greece and ancient India and in candlelit studies in 18th century Europe. You were participating, without knowing it, in one of humanity's oldest and most enduring conversations. The ancient texts of India contain some of the earliest recorded expressions of this wonder. There is a collection of hymns called the Rig Veda, composed perhaps around 1500 years before the Common Era, give or take a century or two, as these things are difficult to date precisely. Among these hymns is one known as the Nazadiya Sukta, which is sometimes called the Creation Hymn or the Hymn of Creation, and it is a remarkable piece of contemplative poetry that expresses uncertainty about the origins of everything with a kind of gentle honesty that still feels fresh after all these millennia. The hymn describes a state before creation, when there was neither existence nor non-existence, neither air nor sky beyond it, and it asks who or what stirred things into being. And then, in lines that have a softness and a humility about them, the hymn admits that perhaps no one really knows. Who really knows? The ancient poet wrote. Who will here proclaim it? Whence was it produced? Whence is this creation? Perhaps it formed itself. Or perhaps it did not. The one who looks down on it from the highest heaven, only that one knows. Or perhaps even that one does not know. There is something restful in encountering such ancient uncertainty, in knowing that the wise people of long ago did not pretend to have all the answers. They stood beneath the same stars you can see from your window, or from a quiet place away from the lights of towns and cities, and they wondered just as you have wondered. In the Western philosophical tradition, we often trace the formal asking of this question to a thinker named Parmenides, who lived in a Greek colony called Elea, on the southern coast of what is now Italy, sometime around 500 years before the Common Era. Parmenides was interested in the nature of being itself, with a capital B, which is a philosophical way of talking about the simple fact that things exist. He wrote a poem, because philosophers in those days often expressed their ideas in verse, and in this poem he explored the idea that being simply is, and that non-being, or nothingness, cannot truly be thought or spoken of in any meaningful way. To even say that nothing exists is a kind of contradiction, Parmenides suggested, because if you are talking about something, then you are talking about something, not nothing. This may seem like a puzzle made of words, and in some sense it is. But Parmenides was circling around the same question that has visited so many minds in the quiet hours of the night. Why is there something rather than nothing? Why does being exist at all? And while Parmenides did not answer this question in any final way, he had the distinction of being one of the first people in the recorded Western tradition to ask it with such clarity and persistence. Centuries passed, and many other thinkers took up the question in their own ways, but one formulation has become particularly famous, perhaps because it is so elegantly simple. In the year 1714, a German philosopher and mathematician named Gottfried Wilhelm Leibniz wrote a short work called The Principles of Nature and Grace, based on reason. Leibniz was a remarkable figure who contributed to many fields of human knowledge, and he had a deep interest in understanding why the universe exists and what principles might underlie its existence. In this work, he posed the question in words that have been repeated countless times since. Why is there something rather than nothing? Leibniz asked. For nothing is simpler and easier than something. There is a gentle logic to this formulation that appeals to many people. If you think about it in a certain way, nothingness seems like the simplest possible state of affairs. No things to arrange, no laws to govern, no particles to bump into one another, no time to flow, no space to stretch. Just nothing at all, blank and empty and utterly uncomplicated. And yet here we are, in a universe that is extraordinarily complicated, full of galaxies and stars and planets and oceans and forests and cities and people lying awake at night asking questions. Leibniz found this state of affairs remarkable, as indeed it is, and he wanted to understand why simplicity had given way to all this wonderful and bewildering complexity. Leibniz himself had answers that he found satisfying, involving a necessary being that he identified with what many people call God, a being whose existence explains the existence of everything else. But the question itself has outlived any particular answer, and it continues to be asked by people who arrive at very different conclusions. In the 20th century, a German philosopher named Martin Heidegger took up this question with renewed intensity. In lectures he delivered in the year 1935, which were later published as a book called Introduction to Metaphysics, Heidegger declared that the question of why there is something rather than nothing is the fundamental question of metaphysics. Metaphysics, in case you are wondering, is the branch of philosophy that concerns itself with the most basic nature of reality, with questions about what exists and what it means for something to exist at all. Heidegger believed that this question about being and nothingness was not merely one philosophical question among many, but was in some sense the deepest question that a human being could ask, the question that lies beneath all other questions. You need not agree with everything Heidegger thought, or with anything Heidegger thought, to find something true in this idea. When you were a child lying in bed, you were not thinking about metaphysics or philosophy or the history of ideas. You were simply thinking, in your own way, about the strangeness of existence. And yet you had arrived, by yourself, at the same place that these great thinkers had arrived. The question is that natural, that close to the bone of human experience. But let us step outside for a moment, away from books and lectures and ancient hymns, and look up at the night sky. If you are in a place without too much artificial light, a place where the stars can be seen properly, you might be able to count roughly 3,000 of them with your unaided eye on a clear night. 3,000 points of light, give or take, scattered across the dome of the sky like grains of salt on a dark tablecloth. Each one of those points is a sun, a great ball of nuclear fire burning steadily in the darkness, most of them much larger and brighter than our own sun, and each one of them is unimaginably far away. The nearest of them is so distant that its light, traveling at 300,000 kilometers per second, takes more than 4 years to reach your eyes. And each one of those stars exists. Each one is there, burning away, doing its stellar thing, being a sun for whatever planets might circle it. And if you pick any one of those 3,000 visible stars and ask yourself why it is there, you find yourself drawn back into the same question you asked as a child. Why is there anything at all? Why this star? Why any star? Why a universe capable of producing stars in the first place? It is worth sitting with this thought for a while, letting it settle into your mind without rushing toward any conclusions. The question is not one that demands an immediate answer. It is more like a companion, a gentle presence that walks beside you when you are in a contemplative mood. You do not need to solve it tonight, or any night. You simply need to let yourself feel the weight and the wonder of it. The ancient poets felt this wonder. Parmenides felt it. Leibniz felt it. Heidegger felt it. Children in their beds feel it still, staring at their ceilings and sensing, perhaps for the first time, that existence is not something to be taken for granted. And now, as you lie here in your own quiet space, you can let this question rest gently in your mind, not as a problem to be solved, but as a companion for the evening. The stars are still out there, burning. The universe is still here, existing. And you are part of it, a small arrangement of matter and energy that somehow has the capacity to wonder about its own presence. There is no hurry. The question has been waiting for thousands of years. It can wait a little longer while you drift toward sleep, held gently by the mystery that has held so many minds before yours. Let us take a moment now to simply consider what is here, to gently survey the contents of existence as we currently understand them, and to appreciate, in the quietest possible way, the sheer scope of what requires explanation when we ask why there is something rather than nothing. This is not an exercise in overwhelm, but rather a peaceful inventory, a calm accounting of the furniture of reality, taken at the pace of a slow walk through a familiar garden where each plant, though seen many times before, still rewards patient attention. We begin with the observable universe, which is to say that portion of all that exists from which light has had sufficient time to reach us since the beginning of cosmic expansion. This observable portion, our visible bubble within what may be a vastly larger or even infinite totality, contains within it a number of galaxies that astronomers have worked diligently to estimate. In a study published in 2016, a team led by Christopher Cancellis at the University of Nottingham applied mathematical models to the deep survey data accumulated over decades of careful observation, and they concluded that the observable universe contains approximately 2 trillion galaxies. That number, written out, is 2 followed by 12 zeros, or 2 million individual galaxies, each one a gravitationally bound system of stars, gas, dust, and the mysterious substance we call dark matter, all orbiting a common center. To sit with that number for a moment, as one might sit with a cup of tea that is still too warm to drink, is to allow the mind to soften around a quantity that defies intuitive grasp. 2 trillion galaxies, scattered across the observable cosmos like seeds dispersed by an unimaginably patient hand, and yet this scattering is not random, as we shall see, but follows patterns and structures that reveal deep regularities in the laws governing existence. Within these galaxies reside stars, the nuclear furnaces that convert hydrogen into heavier elements and, in doing so, release the light that makes the universe visible to itself through the eyes of creatures like us. The total number of stars in the observable universe is estimated, though the estimate carries significant uncertainty, at roughly 10 to the power of 24. This is a 1 followed by 24 zeros, or approximately 1 trillion stars. Some of these stars are far more massive than our Sun, burning hot and blue and exhausting their fuel in mere millions of years, while others are small and red and miserly with their energy, capable of shining steadily for trillions of years into a future we can scarcely imagine. Our own star, the Sun, is a rather ordinary yellow dwarf, middle-aged at approximately 4.6 billion years, and possessing perhaps another 5 billion years of stable hydrogen burning before it swells into a red giant and eventually sheds its outer layers to become a cooling white dwarf ember. If we descend further in scale, from galaxies to stars and now to the atoms that compose the matter of stars, planets, gas clouds, and living beings, we arrive at another staggering estimate. The observable universe is thought to contain approximately 10 to the power of 80 atoms, a number so large that it serves more as a placeholder for incomprehensibility than as a quantity one could ever meaningfully count. These atoms are predominantly hydrogen, the simplest element, followed by helium, which was produced in great abundance during the first few minutes after the initial expansion in a process called Big Bang nucleosynthesis. The heavier elements, including the carbon in our bodies, the oxygen we breathe, the iron in our blood, and the calcium in our bones, were forged in the cores of stars or in the cataclysmic explosions that mark the deaths of massive stars, processes that scattered these elements across space to be incorporated into new generations of stars and planets. Our planet orbits the Sun in the inner reaches of a planetary system that includes 7 other major planets, numerous dwarf planets, moons, asteroids, and comets. This solar system, which seems so vast from our human perspective, requiring years of travel for our fastest spacecraft to reach its outer regions, occupies an almost insignificant volume within our home galaxy, the Milky Way. The Milky Way is a barred spiral galaxy, containing somewhere between 100 billion and 400 billion stars, depending on how one counts the faint and difficult to detect red dwarfs that may constitute the majority of the stellar population. Our solar system lies within one of the spiral arms, specifically the Orion Arm or Orion Spur, at a distance of approximately 26,000 light-years from the galactic center. To speak of 26,000 light-years is to invoke a unit of distance defined by the speed of light, which travels at approximately 300,000 kilometers per second in vacuum. A light-year is the distance that light covers in 1 year of travel at this speed, and it works out to roughly 9.46 trillion kilometers. Our distance from the galactic center, therefore, is a number that might be written as approximately 246 quadrillion kilometers, though such conversions serve mainly to demonstrate why astronomers prefer the more manageable language of light-years. At this distance from the center, our solar system orbits the galaxy at a speed of about 220 kilometers per second, requiring approximately 230 million years to complete a single orbit, a period sometimes called a galactic year or cosmic year. The Milky Way itself is not isolated but exists as part of a small gathering of galaxies known as the Local Group, which contains more than 80 galaxies spread across a volume roughly 10 million light-years in diameter. The largest members of the Local Group are the Milky Way, the Andromeda Galaxy, which is slightly larger and lies approximately 2.5 million light-years distant, and the Triangulum Galaxy, which is somewhat smaller. These major spirals are attended by numerous smaller satellite galaxies, including the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere and which orbit our galaxy like attendants accompanying a modest dignitary. The Local Group, in turn, is situated on the outskirts of a much larger structure known as the Virgo supercluster, which contains perhaps 100 galaxy groups and clusters spread across a volume some 110 million light-years in diameter. And even this supercluster is merely a component of an even grander structure called Laniakea, identified and named in 2014, which encompasses the Virgo supercluster and several neighboring superclusters in a basin of gravitational attraction spanning some 520 million light-years. At the largest scales that we can map, the universe reveals a distinctive architecture that has been called the cosmic web, a vast network of filaments and walls composed of galaxies and galaxy clusters, separated by immense voids where matter is sparse. This structure has been painstakingly charted by surveys such as the Sloan Digital Sky Survey, which began systematic observations in 2000 and has since mapped the positions and distances of millions of galaxies, revealing the foamy, web-like texture of the cosmos. The filaments of the cosmic web are the largest known structures in the universe, some of them stretching across hundreds of millions of light-years, and they trace the gravitational scaffolding along which matter accumulated in the billions of years following the initial expansion. One of the most profound images in the history of astronomy was captured in December of 1995, when the Hubble Space Telescope was directed toward a tiny patch of sky in the constellation Ursa Major, a region that appeared essentially empty to ground-based telescopes, showing no noteworthy stars or nearby galaxies. Over the course of 10 consecutive days, the telescope accumulated light from this seemingly blank region, and the resulting image, known as the Hubble Deep Field, revealed approximately 3,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length. These galaxies ranged from nearby spirals and ellipticals to distant, irregular smudges of light emitted when the universe was less than 1 billion years old. The Hubble Deep Field demonstrated, with quiet eloquence, That what appears empty to casual observation is in fact filled with structure and with light that has traveled billions of years to reach us, and that the universe is populated with galaxies in essentially every direction we care to look. The light from the most distant galaxies visible in such deep field images has been traveling toward us for more than 13 billion years, which means that we see those galaxies as they were in the remote past, when the universe was young and galaxies were still assembling from smaller clumps of matter. But there is a limit to how far back we can see with ordinary light, because before a certain epoch the universe was too hot and dense for light to travel freely. In those early conditions, matter existed as a plasma of free electrons and atomic nuclei, and photons of light scattered constantly off the free electrons, unable to travel any significant distance before being redirected. Only when the universe had cooled sufficiently, approximately 380,000 years after the initial expansion, did electrons and nuclei combine to form neutral atoms, and only then did the universe become transparent to light. The light released at that moment of transition, the first light that could travel freely through space, has been journeying toward us ever since, stretched by the expansion of the universe from its original visible wavelengths into the microwave portion of the electromagnetic spectrum. This ancient light was discovered in 1965 by Arno Penzias and Robert Wilson, two physicists working at Bell Telephone Laboratories in New Jersey, who detected a persistent microwave signal coming from all directions in the sky, a signal that could not be attributed to any known source, and that turned out to be the cosmic microwave background radiation, sometimes described as the afterglow of the hot, dense state from which our universe emerged. The discovery of this radiation provided powerful confirmation of the Big Bang model and earned Penzias and Wilson the Nobel Prize in Physics in 1978. The cosmic microwave background has since been studied with increasingly precise instruments, most recently the Planck satellite, which was launched in 2009 and released its primary results in 2013. The Planck observations revealed that the universe is remarkably uniform in temperature when viewed at these microwave wavelengths, differing from place to place by only about 1 part in 100,000. These tiny temperature variations, however, are profoundly significant, because they trace the subtle density fluctuations in the early universe that eventually grew, under the influence of gravity, into the galaxies, clusters, and cosmic web that we observe today. Among the many findings of the Planck mission was a refined measurement of the composition of the universe, which turns out to be rather humbling for those of us made of atoms. Ordinary matter, the protons, neutrons, and electrons that constitute stars, planets, gas clouds, and living beings, accounts for only about 5% of the total energy content of the universe. Another 27% consists of dark matter, a form of matter that does not emit or absorb light but whose gravitational influence can be detected through its effects on visible matter and on the bending of light from distant sources. The remaining 68%, the majority of the universe's content, is attributed to dark energy, a deeply mysterious component that appears to be causing the expansion of the universe to accelerate, driving galaxies apart at an ever-increasing rate. And so we arrive at a picture of existence that is at once staggeringly vast and delicately structured, richly populated with matter and energy arranged in patterns that span billions of light-years, and yet composed mostly of substances whose fundamental nature remains unknown to us. 2 trillion galaxies, 10 to the 24th power stars, 10 to the 80th power atoms, a cosmic web of filaments and voids, a pervasive bath of ancient microwave light, and beneath it all, The ordinary matter we can see and touch comprising only 1 part in 20 of the whole. All of this exists. All of this is here, surrounding us, extending in every direction to distances the mind cannot truly fathom, persisting through time that stretches back nearly 14 billion years and forward into an uncertain but perhaps eternal future. And it is all of this, every atom and every galaxy, every photon of ancient light and every mysterious quantum of dark energy, that our question addresses when we ask, in the gentlest and most wondering of tones, why there is something rather than nothing at all. Let us now turn our attention to a rather curious matter, one that may at first seem deceptively simple, and that is the question of what nothing actually is, or what nothing would look like if we could somehow encounter it, or whether nothing is even the sort of thing that could exist at all. This is the kind of question that philosophers have pondered for millennia, and it is the kind of question that physicists have more recently begun to examine with their instruments and equations. And what both groups have discovered, in their own ways, is that nothing is far more complicated than one might initially suppose. When we use the word nothing in everyday conversation, we typically mean something rather modest. We mean an absence of particular things, an empty room perhaps, or an empty cupboard, or the disappointing discovery that there is nothing good to watch on television this evening. But these are not examples of true nothing at all. The empty room still contains air, and the air contains countless molecules of nitrogen and oxygen and trace amounts of other gases. And even if we were to remove all the air, the room would still contain space itself, 3 dimensions extending in their familiar directions, and time would continue to pass within it, and the laws of physics would continue to operate there, governing how light would travel through the emptiness and how any object introduced into the space would behave. So what we casually call nothing is really just a local absence of the particular things we were hoping to find, set against a vast backdrop of things that remain very much present. The ancient Greeks thought deeply about this problem, as they thought deeply about so many things, and they arrived at various conclusions that shaped Western philosophy for centuries to come. The atomists, including the philosopher Democritus who lived in the 5th century before the Common Era, proposed that the universe consisted of tiny indivisible particles, which they called atoms, moving through an empty void, which they called kenon in their language. This void was necessary for their theory, because if everything were completely full of matter, with no gaps whatsoever, then movement would be impossible, since there would be no empty space into which anything could move. The kenon was therefore the prerequisite for change, the blank canvas upon which the dance of atoms could take place. But not all Greek thinkers were comfortable with this idea. Aristotle, who came a generation or two after Democritus, was deeply suspicious of the void, and he argued against its existence with considerable vigor, although we shall discuss his arguments calmly and without vigor ourselves. Aristotle observed that if a void existed, there would be no reason for objects within it to move in any particular direction rather than another, since the void by definition had no properties that could distinguish one direction from another. He also reasoned that in a void, with no resistance to movement, objects would move infinitely fast, which seemed absurd to him. And so Aristotle concluded, in a phrase that has echoed down through the centuries, that nature abhors a vacuum. The natural world, in his view, was fundamentally full, and emptiness was not merely rare but actually impossible. This Aristotelian view held sway for a remarkably long time, through the Roman period and the medieval era and into the early modern age. It was not until the 17th century that experimental evidence began to challenge the ancient certainty that vacuums could not exist. The crucial experiment was conducted in the year 1643 by an Italian scientist named Evangelista Torricelli, who had been a student and colleague of the great Galileo. Torricelli filled a long glass tube, sealed at one end, with mercury, which is a dense silvery liquid metal, and then inverted the tube and placed its open end in a dish of mercury. What he observed was that the mercury in the tube fell partway down, leaving a space at the top of the tube above the mercury column. This space, Torricelli reasoned, must be a vacuum, because there was nothing in it, nothing that could be detected anyway. And yet nature had allowed it to form quite readily, without any apparent abhorrence at all. This mercury-filled tube became the first barometer, useful for measuring atmospheric pressure, but its philosophical significance was perhaps even greater than its practical applications. Torricelli had demonstrated that Aristotle was wrong, that empty space could indeed exist within the natural world. And this opened the door to new ways of thinking about the void. Over the following decades and centuries, scientists developed increasingly sophisticated vacuum pumps, capable of removing more and more air from sealed containers, creating emptier and emptier spaces for study and experimentation. But here is where the story takes an interesting turn, and where we must adjust our understanding of what emptiness really means. As physics advanced through the 19th and 20th centuries, it became clear that removing all the air from a container does not leave you with true nothing. Even a perfect vacuum in the classical sense, with every atom and molecule evacuated, still contains several things that are not so easily removed. It contains space itself, with its 3 dimensions and its geometric properties. It contains time, flowing ever forward in its patient way. It contains various fields, including the electromagnetic field that pervades all of space, and the gravitational field that curves and shapes the fabric of space-time. And it contains something else. Something that only became apparent with the development of quantum mechanics in the early 20th century, and that is the restless seething of quantum fluctuations. The theoretical foundation for understanding these fluctuations was laid in 1927 by the German physicist Werner Heisenberg, who formulated what has come to be known as the uncertainty principle. This principle states that there are certain pairs of physical properties, such as position and momentum, or energy and time, that cannot both be measured with arbitrary precision simultaneously. The more precisely you know one member of the pair, the less precisely you can know the other, and this is not a matter of inadequate instruments or clumsy measurement techniques, but rather a fundamental feature of nature at the quantum scale. One consequence of the energy-time version of the uncertainty principle is that over very short intervals of time, the energy of a system can fluctuate by small amounts, borrowing energy from nowhere in particular and then paying it back before anyone can catch the violation of energy conservation in the act. What this means for empty space is rather remarkable. Even in a region where there are no particles of matter, no photons of light, nothing that we would ordinarily call stuff, the quantum fields that fill all of space are constantly fluctuating. These fluctuations manifest as virtual particles, pairs of particles and antiparticles that pop into existence for the briefest of moments before annihilating each other and vanishing again. They are called virtual because they exist for such short times and in such confined circumstances that they cannot be directly observed in the usual sense. But they are not merely theoretical conveniences or mathematical fictions. They have real physical effects that can be measured and confirmed. The most famous demonstration of the reality of these vacuum fluctuations is a phenomenon called the Casimir effect, which was predicted in 1948 by the Dutch physicist Hendrik Casimir. The effect involves two uncharged conducting plates placed very close together in a vacuum. According to classical physics, there should be no force between them, since they carry no electrical charge and are not magnetized. But Casimir calculated that the quantum vacuum fluctuations would be slightly different in the narrow gap between the plates compared to the open space outside them. Certain wavelengths of fluctuation would be excluded from the gap because they would not fit properly between the plates, rather like how certain wavelengths of sound are excluded from a pipe of a particular length. This difference in fluctuations would result in a small but measurable force pushing the plates together. For nearly half a century, the Casimir effect remained a theoretical prediction, elegant and interesting but not experimentally confirmed with high precision. Then in 1997, a physicist named Steve Lamoreux conducted a careful experiment at the Los Alamos National Laboratory in the United States, measuring the force between closely spaced surfaces with exquisite sensitivity, and he found that the force was exactly as Casimir had predicted. The vacuum, it turns out, is not truly empty. It has energy, it has structure, it has physical effects, and these can be measured with sufficiently delicate instruments. This brings us to a more recent contribution to the discussion. The book published in 2012 by the physicist Lawrence Krauss, which bore the provocative title A Universe from Nothing. In this book, Krauss argued that the laws of quantum mechanics and general relativity, combined with certain features of inflationary cosmology, might explain how the universe could have arisen from a state of nothing. The vacuum fluctuations we have been discussing, he suggested, could under certain circumstances give rise to entire universes, bubbling into existence from the seething quantum foam. The book was widely read and much discussed, and it sparked a considerable philosophical debate about what the word nothing actually means. Several philosophers pointed out that the nothing Krauss was describing was not really nothing in the deepest philosophical sense. His nothing still contained space, or at least the potential for space. It still contained quantum fields and the laws of physics that govern how those fields behave. It still contained the framework within which fluctuations could occur and particles could appear. A true nothing, these critics argued, would have none of these things. A true nothing would have no space, no time, no fields, no laws, no potential for anything at all. And this is where we arrive at the most profound difficulty with the concept of nothing, which is that true nothing, absolute nothing, nothing with a capital N, may be literally inconceivable. Whenever we try to imagine it, we find ourselves imagining something, a dark emptiness perhaps, or a blank expanse, but darkness and blankness are themselves qualities, and an expanse has spatial properties, and we are still thinking about something rather than nothing. Our minds seem to be constitutionally incapable of grasping the absence of everything, including the absence of the framework within which presence and absence are defined. Some philosophers have suggested that this difficulty is not merely psychological but logical. Perhaps true nothing is not just hard to imagine but actually impossible. Perhaps the question of why there is something rather than nothing contains a hidden assumption, namely that nothing is a coherent alternative to something, and perhaps this assumption is mistaken. If true nothing is impossible, then the question of why there is something rather than nothing dissolves, because there was never any possibility of nothing to begin with. Others take a different view, arguing that true nothing is at least coherent as a concept, even if we cannot easily picture it, and that the question of why there is something remains meaningful and important. The debate continues, as philosophical debates tend to do, without any final resolution but with plenty of careful reasoning along the way. What we can say with some confidence is that the nothing of physics, the vacuum of quantum field theory, is not the nothing of philosophy. The physicist's vacuum is a busy place, full of potential and fluctuation and subtle energies, and it exists within a framework of space and time and physical law. If there were ever a state of true philosophical nothing, we have no evidence of it, and we have no clear way of even formulating the question of how something could have emerged from it. For emergence implies change, and change implies time, and time is itself something rather than nothing. And so, as you lie there in the comfortable darkness of your room, you might reflect on how mysterious emptiness turns out to be. The space around you, the space between your furniture and within your lungs, the space between the atoms that make up your body, all of it is filled with quantum fields and their ceaseless fluctuations, with virtual particles winking in and out of existence on timescales too short to measure directly, with the subtle residual energy of the vacuum itself. True nothing, it seems, is either very far away indeed or perhaps not anywhere at all. The universe, as it turns out, keeps very good records indeed, and if you know where to look and how to listen, you can find traces of its earliest moments still drifting through the darkness between the stars, faint whispers of light that have been traveling toward us for nearly 14 billion years, patient and unhurried, carrying information about a time when everything that now exists was compressed into a state of unimaginable density and heat, before there were galaxies or stars or planets or the quiet room where you are resting now. And this is perhaps one of the most remarkable discoveries in all of human thought, that the cosmos has not erased its own history but has instead preserved it in subtle forms that we have only recently learned to read, like finding an ancient manuscript written in a language no one spoke anymore until someone finally cracked the code. The story of how we came to understand that the universe had a beginning at all is itself a gentle tale of patient observation and careful reasoning, unfolding over decades through the work of astronomers and physicists who pieced together clues from distant light and mathematical equations. And it starts perhaps most notably with a Belgian priest and physicist named Georges Lemaitre, who in 1931 proposed something that must have seemed quite extraordinary at the time: the idea that the entire universe might have originated from what he called a prime val atom, a single point of immense density from which everything expanded outward, carrying space itself along with it like the surface of a balloon being slowly inflated. And Lemaitre, who had studied both theology and physics with equal devotion, approached this question not with dramatic proclamation but with the quiet confidence of someone following an equation to its logical conclusion, trusting that the mathematics would reveal something true about the nature of things. And he was right, though it would take many more years and many more observations before the scientific community came to accept what he had glimpsed. The observational foundation for this expanding universe had actually been laid just 2 years earlier, in 1929, by an American astronomer named Edwin Hubble, who spent long nights at the Mount Wilson Observatory in the mountains above Los Angeles, peering through what was then the largest telescope in the world, a great instrument with a mirror 100 inches across that gathered light from galaxies so distant they appeared as nothing more than faint smudges against the blackness. And Hubble, through painstaking measurements of these dim patches of light, discovered something that would change our understanding of the cosmos forever, which was that nearly every galaxy he observed was moving away from us, receding into the distance at speeds that increased the farther away the galaxy was located, as if the entire fabric of space were stretching in all directions at once. And this relationship between distance and velocity, now called Hubble's law, provided the first concrete evidence that the universe was not static and eternal as many had assumed, but was instead dynamic and changing, expanding outward from some earlier, denser state. And you can imagine Hubble there in the dome of the observatory, surrounded by the quiet hum of the telescope's mechanisms and the vast California night, carefully recording numbers in a logbook that would eventually help rewrite our cosmic story. If the universe is expanding now, then it follows with simple logic that it must have been smaller in the past. And if you trace this expansion backward through time, rewinding the cosmic film as it were, you eventually arrive at a moment when all the matter and energy we can observe would have been concentrated together in an extraordinarily hot and dense state. And this is what we call the Big Bang, though the name is perhaps a bit misleading because it suggests an explosion outward into pre-existing space, when in fact it was space itself that was expanding, with matter and energy carried along for the ride. And there was no outside into which the universe was expanding because the universe was and is everything, all of space and time together. So it is better to think of it not as an explosion but as a kind of unfolding, a gradual stretching and cooling that allowed the universe to evolve from one state to another, from impossibly hot and dense to the vast and mostly empty cosmos we inhabit today, where galaxies drift like islands separated by unimaginable gulfs of darkness. The thermal history of this expansion is something we have come to understand with remarkable precision, and it unfolds in stages that span immense ranges of time and temperature, though in the early moments things happened very quickly indeed. And one of the most important chapters in this history occurred approximately 380,000 years after the initial expansion began, which sounds like a very long time by human standards, but is really just a brief moment in the cosmic scale. And during this period, the universe had cooled enough that electrons could finally settle into stable orbits around atomic nuclei, forming the first complete atoms, mostly hydrogen and helium with traces of lithium. And before this moment, the universe had been filled with a dense plasma of charged particles that scattered light in every direction, making it opaque like fog. But once atoms formed, the light was free to travel unimpeded through space, streaming outward in all directions. And this light has been traveling ever since, stretched by the expansion of the universe to longer and longer wavelengths until it now reaches us not as visible light but as microwave radiation, very faint and very cold, with a temperature of just 2.725 Kelvin, which is only a few degrees above absolute zero, the coldest anything can possibly be. And this ancient light is called the cosmic microwave background radiation, and it fills the entire universe like a gentle glow, the oldest light we can ever hope to see, a kind of baby picture of the cosmos taken when it was less than 500,000 years old. The existence of this cosmic microwave background was predicted before it was discovered, which is one of those satisfying moments in science when theory precedes observation and is then confirmed by it. And the radiation was first detected accidentally in 1965 by two radio astronomers in New Jersey who were puzzled by a persistent hiss in their antenna that they could not eliminate no matter which direction they pointed it. And only later did they realize they had stumbled upon the remnant light from the early universe, filling the sky in every direction with equal intensity. And for this discovery they eventually received the Nobel Prize. And in the decades that followed, scientists built increasingly sophisticated instruments to study this ancient light in ever greater detail, including a satellite called COBE, which stands for Cosmic Background Explorer, that was launched in 1989 and spent several years mapping the cosmic microwave background from orbit, far above the interfering effects of Earth's atmosphere. The results from COBE, announced in 1992 by a team led by George Smoot and John Mather, revealed something both expected and extraordinary, which was that the cosmic microwave background was not perfectly uniform but contained tiny fluctuations, minuscule variations in temperature from one patch of sky to another, differences so small they amounted to only a few hundred thousandths of a degree. And yet these tiny ripples were profoundly important because they represented the seeds of all the structure we see in the universe today. The slight variations in density in the early universe that would eventually grow under the influence of gravity into galaxies and clusters of galaxies, and the vast cosmic web of filaments and voids that we observe with our telescopes. And without these fluctuations, the universe would have remained a featureless expanse of gas, too smooth and uniform for anything interesting to form. No stars, no planets, no life, no quiet bedrooms where someone might lie resting and wondering about the nature of things. And for their work in measuring these cosmic ripples, Smoot and Mather were awarded the Nobel Prize in Physics in 2006, a recognition of how fundamental their discovery was to our understanding of cosmic origins. The precision of our measurements has only increased since then, with the launch of subsequent satellites including the Planck Space Telescope, which operated from 2009 to 2013 and produced the most detailed maps of the cosmic microwave background ever made, revealing the pattern of hot and cold spots across the sky with exquisite accuracy. And from this data, scientists have been able to determine the age of the universe with remarkable certainty, placing it at approximately 13.8 billion years old, with an uncertainty of only a few tens of millions of years, which may sound like a large margin of error in everyday terms, but is actually extraordinarily precise when you consider the immense spans of time involved. And this age is determined not by any single measurement but by fitting the observed pattern of fluctuations to detailed mathematical models of how the universe evolved from its initial state, adjusting the parameters until the theoretical predictions match the observed data. And the fact that we can do this at all, that we can measure the temperature of light that has been traveling for nearly 14 billion years and use it to reconstruct the conditions that existed when the universe was less than 1,000th of its current age, is a testament to both the ingenuity of human thought and the surprising intelligibility of the cosmos. One of the most puzzling aspects of what these measurements reveal is the extraordinary precision of the initial conditions that gave rise to our universe. The seemingly arbitrary numbers that describe the density and expansion rate and other properties of the early cosmos, which turn out to be tuned with almost unbelievable accuracy. And the physicist and mathematician Roger Penrose, who spent many years thinking about the geometry of space and time, calculated that the initial conditions of our universe appear to have been selected from among all possible configurations with a precision of approximately 1 part in 10 to the power of 60, which is a number so large that it is difficult to convey its meaning, a 1 followed by 60 zeros, representing the odds against our particular universe arising by chance from random initial conditions. And while there is much debate about what this fine-tuning means and whether it requires an explanation at all, it remains one of the most striking features of our cosmic history, that the universe began in a state so precisely arranged that even tiny deviations would have resulted in a cosmos where galaxies could not form or where the expansion would have been too rapid for anything to coalesce. And yet here we are, in a universe that appears almost unreasonably hospitable to the emergence of complexity. It is worth pausing here to note, gently and without any attempt at drama, that everything we have discussed so far describes what happened after existence began, the thermal history and expansion and formation of atoms and galaxies, but it does not and cannot tell us why there was something to expand in the first place, why there was energy in space and the laws of physics rather than nothing at all, and the Big Bang, for all its explanatory power, is not actually a theory of origins in the deepest sense, but rather a description of how the universe evolved from an extremely hot and dense state. And when we trace things back to the very first moments, we eventually reach a point where our current physical theories break down, where the equations give nonsensical answers or require conditions we cannot yet describe. And this is sometimes called the Planck epoch, a period so brief and so extreme that our understanding simply gives out. And beyond this point we cannot say with any certainty what existed or in what form, whether time itself had meaning or whether the concepts we use to describe the universe apply at all. And so the question of why there is something rather than nothing remains unanswered by cosmology, patiently waiting at the boundary of our knowledge like a room we have not yet found the key to enter. And so the universe does indeed remember its beginning, preserving that memory in the faint microwave glow that fills all of space and the particular arrangement of galaxies across the sky. And we have learned to read these records with increasing skill over the past century, building instruments of great sensitivity and developing theories of remarkable subtlety. And yet the deepest question remains, resting quietly beneath all our measurements and calculations. As you rest now, breathing slowly in the dim light. And there is no urgency to this mystery, no deadline by which it must be solved, only the patient presence of the cosmos itself, ancient and vast and somehow here at all. And that is perhaps enough for now, enough to carry you gently toward sleep. In the quieter corners of physics, there exists a realm where the very fabric of reality seems to hum with possibility, where emptiness itself carries within it the seeds of existence, and where the distinction between something and nothing becomes, upon careful examination, rather less clear than we might initially suppose. This is the domain of quantum mechanics, that peculiar and mathematically precise description of nature at its smallest scales, and it offers us perhaps the most unexpected perspective on our fundamental question, suggesting that the emergence of something from nothing may not require any violation of physical law at all, but might instead be precisely what the laws themselves predict. To understand how physicists arrived at this remarkable conclusion, we must first travel back to the year 1928, when a young British physicist named Paul Dirac was working to reconcile two of the great theoretical achievements of the early 20th century, namely quantum mechanics and Einstein's special theory of relativity. The task was formidable because the mathematics of quantum theory, as originally formulated, described particles moving at ordinary speeds, while special relativity demanded that any complete description of nature must remain valid even when objects approach the speed of light. Dirac sought an equation that would describe the electron, that fundamental constituent of atoms, in a manner fully consistent with both frameworks, and after considerable mathematical effort, he succeeded in writing down what is now known simply as the Dirac equation. This equation was immediately recognized as something special, for it not only described electrons correctly but also predicted, entirely of its own accord, certain properties of electrons that had been measured experimentally but never before explained theoretically, such as the precise manner in which electrons behave in magnetic fields. However, the equation also contained something puzzling, something that Dirac himself found initially troubling. When he examined all the mathematical solutions to his equation, he found that alongside the familiar solutions describing electrons with positive energy, there existed equally valid solutions describing particles with negative energy, which seemed to make no physical sense at all. A particle with negative energy would behave in exceedingly strange ways, gaining energy as it slowed down and losing energy as it sped up, which conflicted with everything physicists understood about the natural world. Dirac puzzled over this difficulty and eventually proposed a remarkable interpretation. Perhaps, he suggested, all the negative energy states were already filled, occupied by an infinite sea of electrons that we simply could not observe because they were everywhere and uniform, forming an invisible background to reality. If this were so, then an empty negative energy state, a hole in this sea, would appear to us not as a peculiar negative energy electron but as a particle with positive energy and a positive electric charge, the precise opposite of an electron. Dirac initially hoped this particle might be the proton, which was the only other known fundamental particle at the time, but the mathematics insisted that the whole must have exactly the same mass as the electron, which the proton most certainly does not. The resolution came in 1932, when an American physicist named Carl Anderson was studying cosmic rays, those high-energy particles that continually rain down upon the Earth from outer space. Using a device called a cloud chamber, which reveals the paths of charged particles as trails of tiny droplets, Anderson observed tracks that curved in a magnetic field in precisely the opposite direction from electrons, yet appeared to have the same mass. He had discovered the positron, the anti-electron, the first known example of antimatter. Dirac's equation had predicted the existence of an entirely new form of matter, simply from the requirement that physics obey both quantum mechanics and special relativity. This was a profound moment in the history of science, for it demonstrated that the mathematical structure of physical law could reveal aspects of reality that no one had anticipated, aspects that were nevertheless confirmed when careful observations were made. The discovery of antimatter has deep implications for our question about existence, because it reveals that what we call empty space, the vacuum, is not simply an absence of things but rather a dynamic arena where the rules of quantum mechanics operate continuously. According to quantum field theory, which is the modern descendant of Dirac's work, the vacuum is filled with fields, and these fields are subject to a principle called the uncertainty relation, formulated by Werner Heisenberg, which states that certain pairs of physical quantities cannot both be precisely defined at the same time. One such pair is energy and time, and the uncertainty relation implies that over very short intervals, the energy at any point in space is not fixed but fluctuates, borrowing and returning energy in a ceaseless dance that averages out over longer durations. These fluctuations have measurable consequences. They mean that even in the emptiest possible space, devoid of any matter or radiation, particle-antiparticle pairs are continuously flickering into existence and then annihilating each other, appearing and disappearing far too quickly to be observed directly. These are called virtual particles, and while the term virtual might suggest they are somehow unreal, their effects are genuine and have been confirmed by extraordinarily precise experiments. For instance, the Lamb shift, a tiny adjustment in the energy levels of hydrogen atoms, and the anomalous magnetic moment of the electron, which differs very slightly from the value predicted by simpler theories. Both depend on contributions from virtual particles and both have been measured to agree with theoretical predictions to astonishing accuracy. In 1974, the British physicist Stephen Hawking proposed that these vacuum fluctuations could have dramatic consequences near the event horizon of a black hole, that boundary in space beyond which nothing, not even light, can escape. Hawking reasoned that when a particle-antiparticle pair forms very close to this boundary, it is possible for one member of the pair to fall into the black hole while the other escapes into the surrounding universe. To an outside observer, the escaping particle appears to have been emitted by the black hole itself, And because the energy for this particle must come from somewhere, the black hole gradually loses mass. This process, now known as Hawking radiation, implies that black holes are not entirely black but glow faintly with a thermal spectrum, and that given enough time, they will eventually evaporate completely. While Hawking radiation has not been directly observed, because the effect is extraordinarily weak for any black hole we might actually study, its theoretical derivation is considered a landmark achievement, demonstrating how quantum effects and gravity intertwine in ways we are only beginning to understand. What does all this have to do with why there is something rather than nothing? In 1973, the physicist Edward Tryon published a brief paper in the journal Nature in which he made a startling suggestion. Perhaps, he proposed, the entire universe is nothing more than a vacuum fluctuation, one of those temporary borrowings of energy that quantum mechanics permits, but on a cosmic scale. At first glance this seems absurd, for the universe appears to contain an enormous amount of matter and energy, and vacuum fluctuations are supposed to be fleeting, paying back their borrowed energy almost instantaneously. However, Tryon pointed out something curious about gravity. Gravitational energy is negative, meaning that when you bring matter together, you must add energy to separate it again, which implies that the gravitational energy is a kind of debt. If you add up all the positive energy in the universe, the energy contained in matter and radiation, and then subtract all the gravitational energy, the total might be exactly zero. If this is the case, then the universe contains no net energy at all, and there is nothing to pay back. A vacuum fluctuation that produces a zero-energy universe could, in principle, persist indefinitely. This idea remained somewhat speculative until 1982, when the physicist Alexander Vilenkin at Tufts University developed a more rigorous mathematical treatment of how a universe might emerge from nothing through a process called quantum tunneling. Tunneling is a well-established quantum phenomenon in which a particle can pass through a barrier that classical physics would forbid it to traverse, appearing on the other side without ever having possessed enough energy to climb over. This effect is responsible for radioactive decay, among other things, and is thoroughly confirmed by experiment. Vilenkin showed that the mathematical techniques used to describe tunneling could be applied to the universe as a whole, and that a tiny, closed universe could tunnel into existence from a state of absolute nothingness, a state with no space, no time, no matter, and no energy. The probability of such an event might be small, but in quantum mechanics, small probabilities do not mean impossibility, and over the timeless void of nothingness, the concept of waiting for something to happen becomes meaningless. A year later, in 1983, James Hartle and Stephen Hawking proposed an alternative approach known as the no-boundary proposal. Their idea was to treat the early universe using techniques from quantum mechanics that required rewriting the equations so that time behaved mathematically like a dimension of space. In this formulation, asking what happened before the Big Bang becomes like asking what is north of the North Pole, a question that sounds sensible but reveals itself to be without meaning upon reflection. Time does not begin abruptly at a single moment but emerges gradually, becoming more and more timelike as you move away from the initial state, much as latitude lines on a globe smoothly converge toward a pole without there being a sharp edge. There is no boundary, no first moment, no need for a cause prior to the universe because there is no prior in the usual sense. These proposals, the vacuum fluctuation, the tunneling from nothing, and the no-boundary condition, are not proven facts in the way that the existence of positrons is a proven fact. They are theoretical frameworks, mathematical explorations of what the laws of physics might permit when applied to the universe as a whole. They face formidable difficulties, not least the problem of constructing a complete theory of quantum gravity that would be necessary to evaluate them rigorously. Nevertheless, they represent something remarkable in the history of human thought, for they suggest that the question of why there is something rather than nothing may not lie forever beyond the reach of physics, but might instead be addressed, perhaps even answered, by the same methods that have already revealed so much about the natural world. The recurring theme in all these proposals is that nothing, in the sense of absolute emptiness with no matter, no space, and no time, may be fundamentally unstable under the laws of quantum mechanics. The vacuum is not a static void but a seething potential, and the emergence of universes may be not a violation of natural law but an expression of it. If the total energy of the universe is indeed zero, then something and nothing are, in a precise energetic sense, equivalent, and the universe may have emerged without requiring any net input of existence. This does not tell us why there are laws of physics at all, or why those laws have the particular form they do, but it does suggest that given the laws, the presence of a universe like ours may be entirely natural, perhaps even inevitable. As you rest there, perhaps growing drowsy, you might find some comfort in the thought that emptiness itself contains within it the seeds of being, that the vacuum hums quietly with unborn possibilities, and that even the question of existence, which once seemed so vertiginous and unanswerable, yields slowly to patient investigation, one careful step at a time. Let us turn now to one of the more imaginative possibilities that physicists have considered when thinking about why anything exists at all, and this is the idea that our universe might not be alone, that it might instead be one of an incomprehensibly vast number of universes, each existing alongside the others in some grand ensemble that has come to be called, in the popular imagination at least, the multiverse. This is a word that carries with it a certain weight of science fiction and fantasy, and yet the idea has emerged quite naturally from several different areas of serious theoretical physics, arising independently from quantum mechanics, from cosmology, and from string theory, and it is worth spending some time exploring these possibilities in a calm and measured way, not because we know them to be true, but because they represent genuine attempts by thoughtful people to grapple with the deepest questions about existence itself. The first thread of this multiverse tapestry was woven in the 1950s by a young American physicist named Hugh Everett III, who was working on his doctoral dissertation at Princeton University under the supervision of John Wheeler. Everett was troubled by certain aspects of the standard interpretation of quantum mechanics, particularly the way that measurement seemed to play such a special role in the theory, causing the mathematical object known as the wave function to suddenly collapse into a single definite outcome from among all the possibilities it had been describing. This collapse seemed arbitrary to Everett, an unexplained intrusion of the observer into what ought to be an objective physical description of reality. And so he proposed, in his 1957 thesis, a radically different way of understanding quantum mechanics, one in which the wave function never collapses at all, but instead all the possibilities it describes are equally real, with the universe continuously branching into multiple versions of itself whenever a quantum event occurs that could have multiple outcomes. In Everett's picture, which later came to be called the many-worlds interpretation, when a physicist measures the spin of an electron and finds it pointing upward, there is another version of that physicist in another branch of reality who found the spin pointing downward. And both outcomes are equally real, both physicists equally genuine, each unaware of the other's existence in their separate branches of the universal wave function. The branching happens constantly, at every quantum interaction, producing an unimaginably vast and ever-growing tree of realities, a garden of forking paths where every quantum possibility is realized somewhere. This was a bold proposal, perhaps too bold for its time, and the physics community largely ignored it when it first appeared. Everett, discouraged by the reception of his ideas, left academic physics entirely and spent the rest of his career working on mathematical analysis for the military. He died in 1982, still largely unknown to the broader physics community. But ideas have their own lives, and the many worlds interpretation did not disappear. It was kept alive by a few dedicated physicists, and over the decades it gradually gained more attention and more adherents, particularly as physicists became more comfortable with the strangeness of quantum mechanics and less satisfied with the alternatives. By the end of the 20th century and into the 21st, the many worlds interpretation had moved from the margins to something approaching mainstream respectability, not accepted by everyone, certainly, but taken seriously as one of the leading candidates for understanding what quantum mechanics is really telling us about the nature of reality. Everett's garden of forking paths had finally found its gardeners. A second thread leading to multiverse ideas came not from quantum mechanics but from cosmology, from attempts to understand the very earliest moments of our universe's existence. In the early 1980s, the American physicist Alan Guth proposed a modification to the standard Big Bang theory called inflation, in which the universe underwent a period of extraordinarily rapid expansion in its first fraction of a second, doubling in size again and again in an almost unimaginably short time. This inflationary period helped explain certain puzzling features of the universe we observe today, such as why it appears so uniform in all directions and why its geometry is so remarkably flat. Inflation quickly became a standard part of modern cosmology, but it came with some unexpected implications. Working independently and then in dialogue with each other, the physicists Andrei Linde in the Soviet Union and Paul Stenhardt in the United States developed versions of inflation theory in the 1980s that had a remarkable property, which came to be called eternal inflation. In these models, the inflationary process, once started, never completely stops. While inflation ends in some regions, allowing normal expansion and the formation of galaxies and stars, it continues in other regions, which keep expanding exponentially and spawning new regions where inflation eventually ends, which spawn still more regions, in an endless self-reproducing process. The image that physicists sometimes use is of a foam, a quantum foam of spacetime in which bubbles are constantly forming, each bubble a universe unto itself, with our own observable universe being just one such bubble in an infinite froth of universes, endlessly budding and branching through eternity. In this picture of eternal inflation, the multiverse is not a branching tree of quantum possibilities but rather a vast spatial ensemble, with different universe bubbles existing in different regions of an ever-expanding superspace, each one causally disconnected from the others, unable to send signals or receive information from its sibling universes. We are inside our bubble, and the other bubbles are forever beyond our horizon, unreachable and unobservable, at least by any means we can currently imagine. This is a different kind of multiverse than Everett's quantum branches, arising from different physics, but it shares with Everett's idea the notion that our universe is not unique, that it is one among an enormously large, perhaps infinite, collection of equally real universes. A third thread came from string theory, the ambitious attempt to unify all the fundamental forces and particles of physics in a single mathematical framework based on tiny vibrating strings of energy. In the 1980s and 1990s, string theory seemed to many physicists like the best hope for a final theory of everything, a complete description of the fundamental laws of nature. But as theorists explored the mathematics more deeply, they discovered something troubling, or perhaps exciting, depending on one's perspective. String theory did not seem to predict a unique set of physical laws and constants. Instead, it appeared to allow for an enormous number of different possibilities, different ways that the extra dimensions required by the theory could be curled up and hidden, each configuration corresponding to different values for the fundamental constants of nature, different particle masses, different force strengths, different physics. In 2003, the American physicist Leonard Susskind, building on earlier work by many others, estimated that the number of these different possible configurations, different possible universes with different physical laws, was something like 10 to the power of 500, a number so large that it defies any ordinary comprehension. This vast space of possibilities came to be called the string theory landscape, a metaphor suggesting a terrain of hills and valleys, with each valley representing a different stable configuration of the hidden dimensions and thus a different set of physical laws. If eternal inflation is happening and producing an endless supply of universe bubbles, and if string theory is correct with its landscape of possibilities, then perhaps all these different possible sets of physical laws are actually realized somewhere, in different bubbles, making the multiverse not just spatially vast but also varied in its very physics, a cosmic catalogue of all possible ways a universe might be. This brings us to a curious principle that has been lurking in the background of much of this discussion, a principle that the British cosmologist Brandon Carter first articulated clearly in 1973 and called the anthropic principle. At its simplest, the anthropic principle is almost a tautology, a statement that seems obviously true once you think about it, which is that any universe we observe must have properties that allow for the existence of observers. We cannot find ourselves in a universe where life is impossible, because in such a universe there would be no one to do the finding. This seems trivially true, but Carter and others argued that it might have explanatory power, that it might help explain why the fundamental constants of our universe have the values they do, values that seem in many cases to be finely tuned to allow for the existence of stars, planets, chemistry, and life. If there is only one universe, this fine-tuning seems like an extraordinary coincidence, almost miraculous, and some have taken it as evidence for a cosmic designer. But if there are enormously many universes with different physical constants, then the anthropic principle suggests that we should not be surprised to find ourselves in one of the rare universes where the constants are right for life, because those are the only universes where anyone could be surprised about anything. The anthropic principle, combined with the multiverse, offers a way of explaining the apparent fine-tuning of our universe without invoking miracles or designers. But it comes at the cost of abandoning the hope that the constants of nature can be uniquely predicted from fundamental principles. In 2003, the American physicist Max Tegmark published a useful classification of multiverse theories, organizing them into 4 levels of increasing strangeness and scope. The first level is simply the recognition that our observable universe, the region from which light has had time to reach us since the Big Bang, is probably just a small patch of a much larger universe that extends far beyond our horizon, with regions too distant for us ever to see that contain other galaxies, other planets, perhaps other observers. The second level corresponds to eternal inflation, with its many bubble universes that might have different effective physical constants. The third level is Everett's many worlds interpretation, with its branching quantum realities. And the fourth level, the most speculative of all, suggests that all mathematically consistent structures exist as physical realities somewhere, that every possible universe that can be described by mathematics actually exists. This last level, which Tegmark called the mathematical universe hypothesis, takes us far from conventional physics and into territory that some would call philosophy or even theology. And this brings us to an important caveat that must be acknowledged gently but clearly, which is that most multiverse theories are currently, and perhaps permanently, untestable. If other universes are causally disconnected from us, if we can never receive any signal or evidence from them, then their existence seems to lie beyond the reach of empirical science as traditionally conceived. Some physicists are comfortable with this, arguing that multiverse theories can still be evaluated by their mathematical elegance, their ability to explain features of our universe, and their fruitfulness in generating new ideas. Others are deeply uncomfortable, worrying that we have strayed from physics into metaphysics, from science into speculation dressed in scientific clothing. This debate has divided even physicists who contributed to multiverse ideas in the first place. The Nobel laureate Steven Weinberg was generally favorable toward anthropic reasoning in the multiverse context, arguing that it offered a legitimate explanation for the small but non-zero value of the cosmological constant, the energy density of empty space, which seems fine-tuned in a way that anthropic selection might explain. On the other hand, Paul Stenhardt, who helped develop eternal inflation in the first place, became increasingly critical of the multiverse over the years, arguing that a theory that can accommodate almost any possible observation has no real predictive power and therefore fails as science. This disagreement reflects a deeper tension in theoretical physics about what counts as a good scientific theory, about the relationship between mathematical beauty and empirical testability, about whether we should follow our equations wherever they lead, even if they lead to realms forever beyond observation. These are not easy questions, and they do not have easy answers. And perhaps the most honest thing to say is that we do not yet know whether multiverse theories describe reality or whether they represent a productive path forward or a beautiful dead end. And so we find ourselves in a curious position, having explored these gardens of forking possibilities, these vast ensembles of universes that might or might not exist. The ideas are fascinating, the mathematics often compelling, and the implications profound if any of it is true. But we cannot yet say with confidence that any of it is true, and we may never be able to say so. And that uncertainty is perhaps itself part of the answer to why there is something rather than nothing, or at least part of our ongoing attempt to frame the question correctly. Let us now turn our attention to a rather quieter corner of this vast inquiry, one where we might gently wonder whether the question we have been asking all along has perhaps been posed in the wrong direction entirely. For throughout our contemplation of why there is something rather than nothing, we have been assuming, in that soft and unexamined way that assumptions often settle into our thinking, that nothing was ever a genuine possibility, that the universe might just as easily have failed to exist, that emptiness was waiting in the wings as a real alternative to all this gentle complexity we find around us. But what if, and here we must tread very softly indeed, what if something is not merely what happens to be the case, but what must be the case? What could not have been otherwise? What is in some deep and quiet sense necessary rather than contingent? This distinction between necessity and contingency is one that philosophers have pondered for a very long time, in their unhurried way, often by candlelight or in the gentle quiet of libraries where the dust motes drift through afternoon sun. A contingent thing is something that might or might not exist, something whose absence we can coherently imagine without contradiction, like a particular chair or a specific star, or even, one might think, an entire universe. A necessary thing, by contrast, is something that could not fail to exist, something whose non-existence would involve some kind of logical impossibility, something that simply must be, regardless of circumstances or conditions. And the question we now approach, with all the gentleness appropriate to so profound an inquiry, is whether existence itself, whether the whole fabric of reality, might belong to this second category, might be something that could never have been otherwise. The philosopher Derek Parfit, who spent much of his life at All Souls College in Oxford, where the gardens are particularly peaceful and the pace of thinking particularly unhurried, devoted considerable attention to this question in his later years. In a long and careful essay published in 2011, bearing the simple title Why Anything and Why This, Parfit explored with great patience the logical landscape of possible answers to why there is something rather than nothing. He considered a range of what he called cosmic possibilities, different ways the totality of reality might be structured, and he asked whether any of these possibilities might be more probable than others, or whether one of them might even be uniquely necessary, the only possibility that could coherently be actual. Parfit noticed something rather interesting in his gentle way, which was that among all the cosmic possibilities one might consider, total emptiness, absolute nothingness, is in a certain sense the simplest of all, since it has no features that require explanation, no properties that might have been otherwise, no structure that calls out for further description. And yet, he observed, simplicity alone does not seem to confer any special probability or necessity, for there is no obvious reason why the simplest possibility should be the one that obtains. In fact, Parfit suggested, there might be certain cosmic possibilities that are, in a deeper sense, self-selecting, possibilities that contain within themselves the explanation for their own actuality, possibilities where asking why this rather than something else would somehow miss the point because the answer is already implicit in the nature of the possibility itself. This line of thinking, pursued with the characteristic patience of late-night philosophical reflection, opens the door to an idea that has gained considerable attention among both philosophers and physicists in recent decades: the idea that mathematical structures, those abstract patterns and relationships that mathematicians discover rather than invent, might in some sense exist necessarily, might be the kind of thing that could not fail to be, and might indeed constitute the fundamental fabric of reality itself. The physicist Max Tegmark, who works at the Massachusetts Institute of Technology, where the hallways are long and quiet and conducive to extended contemplation, has developed this idea into what he calls the mathematical universe hypothesis. The proposal, stated as simply as such a profound idea can be stated, is that our physical universe is not merely described by mathematics, in the way that a poem might describe a sunset, but actually is a mathematical structure, identical with one of the countless abstract patterns that exist, if exist is even the right word, in the realm of mathematical possibility. And if this is so, Tegmark suggests, then the question of why there is something rather than nothing dissolves in a rather remarkable way. For mathematical structures do not need to be created or caused or brought into being. They simply are. necessarily and eternally, independent of any physical process or cosmic event. On this view, and it is a view that asks a great deal of our imagination but rewards patient consideration, the universe we inhabit is simply one mathematical structure among infinitely many, all of them equally real in the only sense that matters, all of them existing in that peculiar timeless way that mathematical truths seem to exist, unchanging and uncreated, discovered rather than made. The number 7 did not come into being at some moment and will not cease to be at some future time. It simply is what it is, necessarily and eternally, and the same might be true, Tegmark suggests, of the mathematical structure that we call our universe, the pattern of relationships and symmetries and constants that gives rise to quarks and leptons and the gentle blue of a summer sky. This is not, of course, the only way to approach the idea that something might be necessary rather than contingent, and other thinkers have offered their own gentle variations on this theme. The physicist John Archibald Wheeler, who made significant contributions to our understanding of general relativity and quantum mechanics and who lived to a very great age, continuing his contemplative work well into his 80s and beyond, proposed in 1990 a hypothesis he called it from bit, suggesting that the fundamental fabric of reality might be not matter or energy but information, that the physical universe might emerge from, or perhaps simply be, a vast structure of yes or no answers, of binary distinctions, of pure abstract information. Wheeler imagined, in his gentle and speculative way, that every physical quantity, every particle and field and force, might ultimately derive its existence from what he called observer participancy, from the act of measurement and observation that the universe performs on itself, creating a vast self-referential loop of information and existence that has no need of an external cause or creator. The universe, on this view, brings itself into being through the very act of being observed, through the accumulation of information that constitutes its own reality, and the question of why there is something rather than nothing becomes, in a curious way, a question about the nature of information itself, about whether pure abstract pattern and distinction might be the kind of thing that necessarily exists. Now, there is another approach to this question that we might consider as we settle more deeply into our contemplation, an approach suggested by the philosopher of science Adolf Grunbaum, who spent many years at the University of Pittsburgh, where the winters are long and the libraries are warm and conducive to extended reflection. Grunbaum argued, with considerable patience and logical care, that the very notion of nothing, of absolute emptiness, of the total absence of anything whatsoever, might be far more problematic than we typically assume, might in fact be a concept so laden with hidden difficulties that it cannot coherently serve as a genuine alternative to something. For what would nothing actually be? Grunbaum asked, if we tried to describe it with any precision at all. Would it be empty space, extending infinitely in all directions? But empty space is itself something, a geometric structure with properties and dimensions. And even in the absence of matter, space would constitute a kind of existence, a something rather than nothing. Would it be the absence even of space, the absence of any container or dimension or extension? But then what would distinguish nothing from, say, a single point, or from the number 0, or from any other abstract entity that we might use to characterize it? The very act of describing nothing, of giving it properties like emptiness or absence or simplicity, seems to turn it into something, to give it a character and a nature that pure nothingness ought not to possess. Grunbaum suggested, in his careful philosophical way, that we have perhaps been asking the question backwards all along. We have assumed that nothing is the default state, the natural condition, the thing that requires no explanation, and that something is the puzzle, the deviation, the thing that calls out for a cause. But why should we make this assumption? Why should emptiness be any more natural or self-explanatory than fullness? Indeed, Grunbaum argued, there may be something deeply incoherent about the very concept of nothing, something that makes it not merely improbable but impossible, not merely rare but logically excluded from the space of genuine possibilities. This line of thinking finds an interesting resonance in the work of Frank Wilczek, the Nobel Prize-winning physicist who has spent much of his career studying the fundamental forces of nature and the deep structure of physical reality. Wilczek has observed, with that gentle precision characteristic of the best scientific writing, that empty space in modern physics is not at all what our everyday intuition might suggest, not a passive background of pure absence, but a seething cauldron of quantum activity, a medium alive with virtual particles flickering in and out of existence, with fields oscillating at every frequency, with energy fluctuating on scales too small and too fast for ordinary experience to detect. In the language of quantum field theory, the vacuum, which is the closest thing physics can offer to nothing, is not a state of zero energy but rather a state of minimum energy. And this minimum is not zero at all. It is a positive value, reflecting all the quantum fluctuations that cannot be eliminated even when every particle has been removed. More than this, Wilczek has noted, the vacuum is in a certain sense unstable, or at least delicately balanced, susceptible to decay into states with more particles, more structure, more something. The nothing of physics, if we may call it that, has a natural tendency to become something, to give rise to matter and radiation and all the complexity we observe. And this suggests that something may not be the exception that requires explanation but rather the rule, the natural outcome of whatever lies at the deepest level of reality. This brings us, in our unhurried way, to a final consideration that we might hold gently in mind as we approach the end of this section, a consideration raised by the physicist Sean Carroll, who writes with admirable clarity about the deepest questions in cosmology and philosophy. Carroll has suggested, with the patience appropriate to so fundamental an issue, that the question why is there something rather than nothing may be what philosophers call a malformed question. A question that appears meaningful on its surface but that dissolves into confusion when we examine it more carefully. For the word why, Carroll observes, typically implies a cause, a reason, an explanation of the form this happened because that happened, and this kind of explanation presupposes a framework of time and causation within which events can be related to their antecedents. But time, on our best current understanding, is not a feature of some larger reality within which the universe sits. It is a feature of the universe itself, a dimension of space-time that came into being, if being is even the right word, with the universe. There was no before the universe in which a cause might have operated, no temporal stage on which the drama of creation might have been enacted, no framework of preceding events from which the universe might have emerged. If this is so, Carroll suggests, then asking why there is something rather than nothing may be like asking what is north of the North Pole, a question that uses familiar words in a combination that turns out to have no coherent referent, a question that we can voice without difficulty but that does not actually point to any genuine puzzle requiring solution. The universe may not need a cause in the ordinary sense, may not need an explanation of the form we typically seek, may simply be, In the same way that the laws of logic simply are. In the same way that mathematical truths simply are. Not because of anything but as the foundation on which all because and all explanation ultimately rest. And so we find ourselves, at the end of this gentle exploration, not with a definitive answer but with a softening of the question, a suggestion that the puzzle we began with may be less puzzling than it first appeared, that something may not be the surprising exception but rather the necessary condition, the only coherent possibility, the thing that could not have been otherwise. Perhaps nothing was never a real alternative. Perhaps existence is not contingent but necessary. Perhaps the deepest question in the universe, pondered long enough and patiently enough, simply dissolves, leaving not an answer but a kind of quiet acceptance, a settling into the fact that here we are, that here all this is, that something rather than nothing is simply what must be. And with that gentle thought, we may let our minds rest, secure in the knowledge that the universe, for all its mystery, holds us softly and will not let us fall. And so we arrive, gently, at the place where we began, though perhaps we see it now with slightly different eyes, the way a familiar room appears changed after a long journey, not because anything in the room has moved, but because we ourselves have traveled far and returned with a wider sense of what questions can be asked, and what it means to rest peacefully without demanding that every question receive its answer tonight, or ever. We have wandered together through territories of thought where the greatest minds have paused and wondered, where equations reach toward something just beyond their grasp, where philosophers have sat in quiet contemplation for lifetimes, and where the universe itself seems to hold its breath, neither confirming nor denying the theories we have constructed like careful bridges across an infinite chasm. And now we find ourselves here, in this gentle moment, where the mystery remains as vast as it ever was, and where that vastness need not trouble us, but might instead become a kind of comfort, a soft blanket woven from the very fabric of existence, wrapping around us as we prepare to rest. There is a remark that Albert Einstein made in the year 1930, during a period when he was reflecting not upon his equations or his famous thought experiments, but upon something more fundamental, something that had quietly astonished him throughout his life. And what he said was this: that the most incomprehensible thing about the universe is that it is comprehensible. A statement so simple on its surface and yet so profound in its implications. Because what Einstein was noting, with that characteristic mixture of humility and wonder that marked his later years, was that there is no obvious reason why the universe should make sense to us at all. No guarantee written into the nature of things that a species of upright primates on a small rocky world should be able to look up at the stars and understand, even partially, the laws that govern their burning, the forces that shape their motion, the mathematics that describes the curvature of space and the flow of time. Think of it this way, if you can, as your breathing slows and your body settles more deeply into rest, that we might have evolved in a universe of pure chaos, where cause and effect were unreliable, where the same action might produce different results on different days, where no pattern ever repeated and no law ever held. And in such a universe, there would be nothing to understand, nothing to discover, no science to pursue and no equations to write, only a swirling confusion without meaning or structure. And yet that is not the universe we inhabit. And instead we find ourselves in a cosmos where patterns persist, where mathematics mirrors reality with uncanny precision, where a theory scribbled on paper in Germany can predict the bending of light around the sun and be confirmed years later by astronomers in distant lands. And this correspondence between mind and world, between the symbols we invent and the structures we discover, is itself a mystery as deep as any we have contemplated tonight. Einstein found this comprehensibility astonishing, perhaps even more astonishing than any particular discovery he had made, because it suggested that the universe was somehow disposed toward being known, toward revealing itself to patient inquiry, toward allowing creatures made of matter to understand the laws that govern matter, and whether this disposition is evidence of design or merely a fortunate accident, whether it points toward some deeper purpose or is simply the way things happen to be, we cannot say with certainty, and perhaps we need not say anything at all, but simply notice, with quiet gratitude, that understanding is possible, that we can ask these questions and sometimes receive answers, and that even when the answers do not come, the asking itself is a gift of remarkable and gentle beauty. The astronomer Carl Sagan, who spent his life contemplating the cosmos and sharing that contemplation with millions of others through his soft-spoken and wonder-filled voice, once offered a reflection that has stayed with many who heard it, a reflection on what we are and where we came from. And what he said was that we are star stuff contemplating the stars, a phrase so poetic and yet so literally true that it can take your breath away if you let it. Because the atoms in your body, the carbon in your bones and the iron in your blood and the calcium in your teeth, were all forged in the hearts of stars that burned and died billions of years before the Earth was formed. And those atoms drifted through space as dust and gas until gravity gathered them again into new stars and new planets and eventually into you. Lying here now, breathing gently, thinking about the universe that made you and wondering why there is anything at all. You are, in the most profound and scientific sense, the universe becoming aware of itself. A pattern of matter that has somehow learned to ask questions about matter, a temporary arrangement of atoms that can contemplate the laws governing atoms. And when you look up at the night sky, if you are fortunate enough to see the stars from a dark place far from city lights, you are not merely looking at distant suns but at your own origins, at the forges where your substance was created, at the ancestral fires whose remnants now constitute your very flesh. And this recognition, this deep knowing that we are not separate from the cosmos but woven into its fabric, is what Sagan meant by star stuff contemplating the stars, a phrase that carries within it both the humility of knowing our small place and the dignity of knowing we can comprehend, at least in part, the immensity that surrounds us. The philosopher Ludwig Wittgenstein, who spent his life wrestling with the limits of language and the boundaries of what can be meaningfully said, offered an observation near the end of his most famous work that speaks directly to the question we have been circling all evening. And what he wrote was this: that not how the world is the mystical, but that it is. And in this single sentence he captured something essential about the nature of the deepest wonder. Because science can tell us a great deal about how the world works, about the mechanisms and processes and laws that govern its behavior, about how galaxies form and how cells divide and how light travels through the vacuum of space. But science cannot tell us, or at least has not yet told us, why there is a world at all rather than nothing, why existence exists, why being is rather than is not. And this sheer fact of there being anything, is what Wittgenstein identified as the mystical, not in any supernatural sense but in the sense of something that lies at the very limit of what can be expressed, something that language points toward but cannot quite capture, something we can feel more easily than we can say. And perhaps that is enough, to feel this wonder without needing to explain it, to rest in the mystery without demanding that it resolve itself into a neat formula or a tidy answer, to let the question remain a question, suspended in the quiet darkness like a distant star whose light reaches us across millions of years, carrying information we may never fully decode but which touches us nonetheless. And in this way, the deepest question in the universe becomes not a burden but a companion, not a problem to be solved but a presence to be acknowledged, not a source of anxiety but a gateway to the kind of contemplative peace that asks nothing and receives everything. There is a phenomenon that astronauts have reported, particularly those who have had the opportunity to see the Earth from space, a phenomenon that has come to be called the overview effect, and it refers to the profound shift in perspective and consciousness that often accompanies the experience of viewing our planet as a whole, a small blue marble floating in the infinite blackness, fragile and precious and unspeakably beautiful. And one astronaut who described this experience with particular eloquence was Edgar Mitchell, who traveled to the Moon as part of the Apollo 14 mission in 1971. And what Mitchell reported was not merely a visual experience but something much deeper, a sense of cosmic connection, a feeling that the separations we take for granted between self and world, between one nation and another, between humanity and the rest of existence, were somehow illusory, that everything was interconnected in ways that his scientific training had never prepared him to understand, and that the universe was not the cold and indifferent void that some philosophies had described, but something more like a living system, a single vast organism of which he was a part. Mitchell spent the rest of his life trying to understand and articulate what he had experienced on that return journey from the Moon. As he looked out the window of his spacecraft and saw the Earth and the stars and the darkness all at once. And while different astronauts have described the overview effect in different terms, many have reported similar experiences. A sense of awe and unity, a dissolution of ordinary boundaries. A recognition that the question of why there is something rather than nothing is not merely an intellectual puzzle but a living reality to be felt and inhabited. And perhaps this is one of the gifts of space exploration. Not only the data it returns but the perspective it provides. The reminder that we are small and brief and yet capable of experiences so profound they change us forever. It is worth acknowledging, as we settle more deeply into rest, that current physics may be centuries away from an answer to the question of why there is something rather than nothing, if indeed an answer is possible at all. And there are serious thinkers who believe that this question may transcend science entirely, that it may belong to a category of inquiry that no empirical observation or mathematical proof could ever resolve, because any physical theory, however complete, will still describe the behavior of something that exists, and the question of why existence exists at all lies somehow beneath or beyond the domain of physics, in a territory where perhaps only philosophy or contemplation or silence can go. And this is not a failure of science but simply a recognition of its boundaries. The way a map can show you many things but cannot step off the page and become the territory it represents. And yet the search continues, as it should, because we do not know in advance which questions will yield to inquiry and which will remain forever open. And every generation of scientists pushes a little further into the unknown, extends the reach of our instruments, refines the precision of our theories, and discovers things that previous generations could not have imagined. And so we must hold both possibilities in our minds at once. The possibility that an answer may someday emerge from the equations and the possibility that the mystery may prove permanent. And in either case, the searching itself has value. The wondering itself is worthwhile. The questions themselves are gifts even when the answers do not come. Consider the James Webb Space Telescope, which at this very moment is orbiting the Sun at a point roughly 1.5 million kilometers from Earth. Its golden mirrors collecting light that has traveled across billions of years to reach us. Light that carries information about the earliest epochs of cosmic history, about stars and galaxies that formed when the universe was young and hot and still finding its structure. And already this remarkable instrument has pushed our observations back to a time only 300 million years after the Big Bang, showing us galaxies more distant and more ancient than any we had seen before. And in the years to come it will continue this work, peering ever deeper into the past, approaching ever closer to the moment when the first light emerged from the cooling plasma of the early universe. And though it cannot show us the moment of origin itself, the instant when something emerged from nothing, if indeed that is what happened, it brings us closer than we have ever been. And future missions, instruments not yet built and telescopes not yet imagined, will push further still. And perhaps one day, centuries from now, our descendants will look back on our current understanding as primitive and incomplete, the way we look back on the cosmology of the ancient Greeks, and perhaps they will have answers to questions we have barely learned to ask. But tonight, none of that matters. Or rather, it matters only as a gentle reassurance that the inquiry continues, that humanity has not given up on understanding, that somewhere in observatories and universities and research centers around the world, people are still looking up and still asking why. And this continuity of wonder, this chain of questioning that stretches back through millennia and forward into an unknowable future, is itself a kind of comfort, a reminder that we are part of something larger than ourselves, a species that wonders, a civilization that asks, a form of consciousness that refuses to take existence for granted even when existence refuses to explain itself. And now, as sleep approaches, as your body grows heavy and your thoughts begin to soften around the edges, you might imagine yourself drifting not through darkness but through light, through the gentle glow of 2 trillion galaxies, each one a vast city of stars, each star potentially circled by worlds, each world a mystery unto itself, and all of it, every photon and every particle, every cloud of gas and every burning sun, exists, is here, is real, and no one knows why, and perhaps no one ever will, and perhaps that is exactly as it should be, because some mysteries are not meant to be solved but savored, not meant to be closed but kept open like windows onto infinity, letting in a breeze from somewhere beyond the walls of ordinary understanding. Existence itself, the sheer fact that anything is, becomes in this light not a problem but a gift, the greatest gift, given by no one knows whom to no one knows why, and we are here to receive it, to notice it, to wonder at it, to ask our questions and make our theories and build our telescopes and write our equations, and then, at the end of each day, to rest in the mystery, to let the question hold us rather than demanding that we hold the question, to trust that the universe, in its incomprehensible comprehensibility, is somehow enough, is somehow good, is somehow home. And so the deepest question in the universe becomes, in these final moments before sleep, the gentlest invitation to wonder, not a challenge to be met but a door to be left open, not an ache to be satisfied but a spaciousness to be inhabited. And as your breathing deepens and your awareness softens, you are held by the same forces that hold the galaxies in their courses, by the same existence that animates every particle and every star, by the same mystery that has puzzled sages and scientists for as long as humans have looked up at the sky and asked why. And there is nothing you need to do about this mystery, nothing you need to figure out or solve or resolve, only rest. Only breathe, only let yourself be part of it all. Star stuff contemplating the stars, consciousness cradled by the cosmos, a brief and beautiful pattern in the infinite tapestry of being, drifting now toward sleep, toward dreams, toward the gentle darkness that is not absence but presence in another form. And the question remains, as it has always remained, as it perhaps always will, not as a burden but as a blessing, not as an answer withheld but as a wonder extended. The universe asking itself why it exists and finding, in the asking, something worth existing for.